Hi there, welcome to Explain This, a podcast where we try to explain complex things in simpler ways for people of all ages. I'm your host Jin Kim, and today we're going to tear down and explore the thing that probably runs a significant portion of your life, the computer. And before you at me, your phone is a computer nowadays, unless you still have an old school Nokia brick. I do miss those unbreakable babies. Alright, let's get started. Have you ever stopped to think about what a computer actually is? We use them every single day for work, for play, for connecting with people we love, for doom scrolling through cat videos at 2 a.m. But how do they work? How do you go from silicon chips and circuits and ones and zeros to videos, programs, and even games on the screen? Today we're going to pull back the curtain and reveal that the magic box on your desk or in your hand isn't one single magical entity, but rather a high-end Michelin star kitchen staffed by a team of specialists serving you a delicious meal. What? Oh, that's right. It's time for Jen's extended metaphor ELI 5 time. Grab your apron and let's tour the kitchen, as if you're a child. Imagine you're sitting at a restaurant and you're really hungry for a cat video. So you tap on a button on the table to place an order with the waiter. The waiter rushes your order into the kitchen, where the magic happens. Inside this amazing, super fast kitchen, the head chef gets your order. The head chef is the boss. They're super smart and know how to read all the recipes. The head chef, whose name is CPU, looks at your order and shouts, "One cat video, coming right up." Now the CPU can't just pull a cat out of thin air. He's not that magical. He needs the recipe and the ingredients. The recipe for Funny Cat is stored way in the back in a giant pantry and a massive fridge. This is the computer's storage. A kitchen helper runs to the pantry, grabs the recipe and all the ingredients, and brings them over to the main prep bench. This prep bench is called RAM, like a boy sheep. The CPU can use this space to really cook up a storm. He can grab anything he needs in a flash if it's already in the RAM bench. It's much faster than running back to the pantry every single time he needs a pinch of salt or a whisker. Now, the CPU can't start working. He reads the recipe one line at a time. Step 1, get the color for the left ear. Step 2, calculate the position of the nose. He's incredibly fast, doing billions of these steps every second. He uses all of his fancy kitchen tools, his knives, his whisks, his mixing bowls, to prepare everything perfectly. But making a picture is a huge job. It's like painting a giant mural made of millions of tiny dots of color. The head chef is way too busy and important to paint every single dot himself. That would take forever. So he does something clever. He shouts the simple instructions to a massive team of plating artists. This team is the GPU, or the graphics team. Imagine an army of thousands of artists all standing in front of a giant canvas, which is a screen. The CPU tells them what to do. Artist 1, you paint your dot bright orange. Artist 2, you paint your dot black. Artist 3, another black dot, please. Because there are thousands of them working all at the same time, they can paint the entire beautiful picture of the kitten on the screen almost instantly. And since the kitchen is so blazing fast, it can pump out like 60 of those pictures a second, then show it to you like a flipbook, which makes it a video. And voila! Your adorable and hilarious cat video is served. Of course, none of this could happen without the rest of the kitchen staff. The whole kitchen, with the wires in the walls that let the head chef station talk to the artist station, is called the motherboard. And all the lights, the ovens, the electrical whisks get their power from the building's main power room, which is the power supply. There's also other team members like cooling that cheers the team on with fans and refreshing drinks to keep them cool, and the network card letting Chef CPU access recipes he's never seen before on the internet, and so on. And that's what a computer is. An awesome team all working super hard to help you with your homework, let you message your friends, listen to awesome podcasts like this one, and most importantly, provide you with sweet memes. Alright, I'm not gonna lie. This topic has been a bit of a white whale for the podcast. Trying to explain how computers work feels like condensing a 3-year university degree into a single segment. But I freaking love computers, so let's dive in. As usual, we need to start with the history of how computers came to be. We'll trace the key moments that took us from ancient beads to the magic box in your pocket. So, when do you think the first computer was invented? If we're talking about computing in its purest sense, calculating things, Then our story starts with the abacus, way back in ancient times. An abacus is a fantastically clever tool. Imagine rows of beads. The first row is for ones, the next for tens, then the hundreds, and so on. When you fill up the ones row by reaching 10, you simply carry the 1 over by moving a single bead in the tens row and starting over on the first row. It's a simple concept that was revolutionary for doing maths quickly for centuries, and it's still more reliable than me trying to do mental maths before my first coffee. This idea of computing wasn't just for counting. The word computer was originally a job title. Until the mid-20th century, computers were people, often brilliant women like Katherine Johnson at NASA, who performed complex calculations by hand to send humanity to the moon. But as our maths got more complex, we needed better machines for the maths. This brings us to the 1800s and the father of the computer, Charles Babbage. He designed the machine called the analytical engine. And this is where things get spooky modern. Babbage envisioned his machine having an arithmetic logic unit to do the maths and a memory to store numbers. That sounds familiar? It's because that's the basic blueprint for the CPU in your computer right now. Babbage's machine was never built in his lifetime, the ultimate case of a brilliant project getting stuck in development hell. But his idea captivated a brilliant mathematician named Ada Lovelace. She saw that the analytical engine could be more than just a calculator. She realized that if you could feed it the right instructions, a program, it could do anything. It could process words, create music, or even generate images. Lovelace saw the machine's true general-purpose potential. She even wrote the world's first ever computer program for the analytical engine, making her the first programmer in history, long before the first computer even existed. So, Babbage gave us the architecture and Lovelace gave us the vision. But these machines were still just concepts at that time. The first real leap happened in 1890 with Herman Hollerith's tabulating machine, invented to solve the crisis of the US Census. Counting 63 million people's worth of census by hand was projected to take over a decade. As in, they'd be running the 1900 census before the 1890 census results were even published. Hollerith's electromechanical tabulating machine, catchy name, used electricity and punch cards, an idea Babbage borrowed from weaving looms, to tally results 10 times faster. Holes in the cards completed electrical circuits, which turned the gears and tallied the numbers. Yep, punch cards were the original program software. Oh, by the way, Hollerith's company would end up being IBM. If you've heard of it, it's because it was the biggest computing company in the 1900s. This invention was a huge step, but these early computers were slow and clunky, and they were full of mechanical parts that wore out. A famous story tells of a moth getting stuck in one machine, causing it to fail, which is where we get the term bug. And when programmers needed to fix their punch card programs, they'd literally patch the holes with paper, giving us the term patch. To get faster, we needed to ditch the moving mechanical parts. And the answer was the vacuum tube, which could act as a switch using only electricity. This led to ENIAC in the 1940s, that's ENIAC. It was the first programmable, general-purpose electronic computer. It was an incredible achievement because ENIAC could be programmed to solve all kinds of equations and solve lots of different problems. But it also had many weaknesses and downsides. ENIAC was a 30-ton beast that filled up an entire room, generated immense heat, and it constantly had vacuum tubes burning out like light bulbs. Most importantly, it couldn't even run Doom, let alone Skyrim. To get to the computers we know and love today, the sleek devices on our desks and in our hands, we needed one final miraculous invention, the transistor. Now, we've been talking about the evolution of switches from metal pins to mechanical switches to vacuum tubes to transistors. But what are switches anyway, and why do we need them for computers? Believe it or not, computers are basically a glorified bank of light switches. By flicking light switches on or off in a specific order, based on a very specific set of rules that make even flat-pack furniture assembly instructions look easy, computers can do everything. We'll get more into how switches work in a computer soon, but for now, all you need to understand is that switches need to turn on and off. If there are moving parts, turning a switch on and off billions of times will wear them out into dust. If the switch is made out of a glass tube with electrical wires, it can burn out or break. So, in 1947, a team of scientists at Bell Labs invented a switch that has no moving parts, doesn't burn out, and can be miniaturized into teeny tiny components that can all fit on a circuit board. The transistor. Now, a switch is basically a device that can complete an electric circuit when it is switched on, and then break the circuit when it is switched off. In mechanical switches, it literally puts a piece of copper wire between two ends of a circuit so that electricity can flow through it and complete the circuit. But what if instead of a mechanical switch, we had a special kind of material that could conduct electricity only when it's turned on, as in the whole material itself is a switch? Enter the semiconductor. A semiconductor, like the name suggests, does this exact thing. It sometimes conducts electricity, under specific conditions. Computer chips use silicon as the semiconductor because silicon is dirt cheap and abundant. I mean, it's basically purified sand. Silicon is normally not a good conductor because its electrons are all locked up neatly in a crystal lattice, like a neatly organized shelf of collectible figurines. No touchy, no moody. But scientists figured out that you can make silicon conduct electricity if you add some other chemicals to it, in a technique called, I kid you not, doping. When you dope silicon with phosphorus, you get N-type silicon that has extra electrons making it negatively charged. N stands for negative Nancy. But you can also dope silicon with boron to get P-type silicon. Here you have fewer electrons, so you have pockets or holes that are positively charged, where free electrons can roam. P stands for positive... I don't know, what's the opposite of a negative Nancy? Positive Patty? Anyway, transistors are made up of two pieces of N-type silicon separated by a P-type silicon. Like a silicon sandwich, except it's silicon all the way down. Kind of like a double down sandwich. I don't know, the metaphor is breaking down a bit. Now, normally the border between the two different silicon types, the depletion layer, doesn't conduct any electricity. So, in this state, a transistor is off. No electricity goes through it. But if you place a thin electrode or a gate on top of the P-type silicon filling, and then apply a bit of electricity to the gate, the electric field attracts all of the excess electrons in the N-type silicon ends. The extra electrons get a bit hot and bothered like an angry mob charging the stadium, and they flood the P-type silicon. They fill the holes of positive charge, creating a temporary bridge that lets current flow from one N-type silicon end to the other. Now, the switch is on. As soon as you turn the gate voltage off, the switch turns off. Hooray! We've invented the solid-state silicon switch, or transistor. Cool. So now what? What can we do with these teeny tiny switches? Well, this is where the zeros and ones come in. You've probably heard that computers think and speak in zeros and ones.
Binary solo.
0000001 0000001 1
That was a little excerpt from the song Humans Are Dead by Flight of the Conchords. Wonderful song. Anyway, today is when you finally understand what that really means. Computers do all of their wonderful maths and processing and meme making using switches that can turn on or off. Because you can't have a switch half on, or 67% on, this means there's only two states the switch can be in. In other words, it's a binary system. Binary sounds super restrictive, but you can actually do a lot with them. For example, if you have one switch, you can only say two things, on or off. But what if you have two switches? Now you can have both switches on, both switches off, the left switch on but the right switch off, and vice versa. There, two switches gives us four different expressions. To make things simpler, instead of on or off, we can use numbers. If a switch is on, it's a 1. If it's off, it's a 0. So in our last example, the four options were 1, 1, 0, 0, 1, 0, and 0, 1. Every time we add a switch, we double the number of possibilities. So 1 switch has 2 possibilities, 2 switches equals 4, 3 switches 8, 4 switches 16, and so forth. In essence, the number of possibilities is 2 to the power of the number of switches. We can use this system to count as well. Remember the abacus example at the start of the episode, where when you count to 10, you carry over the 1 to the 10s and reset the 1s? Well, the same thing applies to the binary system. Let's count from 0 to 10 using binary. 0 is easy, just have all of the switches off, so 0, 0, 0, 0. 1 is also easy, just turn the first switch on, 0, 0, 0, 1. But if you want 2, you can't do that on one switch, so you have to carry over the 1 to the next switch. We'd write that as 0, 0, 1, 0. Next is 3. We just have to add another 1, so we go 0, 0, 1, 1. But if we want to count to 4, the first two switches are already filled up, so again, we carry over the 1 to the next switch, and now we have 0, 1, 0, 0. Do you see how this is going? Next is 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, and then 1, 0, 0, 0. Now that you know how bases and binary systems work, you can go the other way too. What's 1011 in normal base 10 number? Well, we start from the right to the left. The first digit, or bit, is equal to 1. The second bit is equal to 2. The third bit is equal to double this, or 4. But since it says 0, we ignore this one. Lastly, the fourth bit is 8, so 1011 is essentially 8 plus 2 plus 1, which is 11. Thankfully, you don't have to be able to do this because computers will know what the binary code is saying and translate it for you. But knowing the system helps us understand a few weird computer maths. Like, for example, if you grew up in the 80s and 90s, you're familiar with the term 8-bit, like 8-bit music and games. 8 bits means there are 8 total switches to work with. This means that there are 2 to the power of 8 possibilities, which is 256. Using an 8-bit system, you can have 256 different answers. In the case of 8-bit music, this means you have 256 different tones. In 8-bit games, there are 256 possible colors that the games can visually represent, which is why old school video games had that gradient look. We call this value, 8 bits, 1 byte. If you have 1,000 of these bytes, that would be a kilobyte, like how kilometer is 1,000 meters. And you've probably heard of kilobytes, because then there's megabytes, which is 1,000,000 bytes, a gigabyte, 1,000,000,000 bytes, and a terabyte, which is 1,000,000,000,000 bytes. The more bits or switches you have, the more data you can store and represent. Your computer or phone probably runs on 64 bits nowadays, which means it can handle data in chunks of 64 bits. How many possibilities is that? Well, surely it's bigger than 256. Let's do the maths. 2 to the power of 64 is... oh, that's 18 quintillion, or 18 with 18 zeros after it. That's a heckin' lot of data. With this system, we can represent any letter, symbol, musical note, or pixel color with a string of zeros and ones. It's kind of like a barcode. Alright, so we can store almost any kind of data using on and off switches. What else can we do? Well, here's where the fun part comes in, the moment you've been waiting for, how CPUs, or central processing units, work. You've probably heard of CPUs, also called processors, described as the brain of your PC. Now, this isn't technically true because your entire computer is like the brain. A better comparison is the kitchen analogy we used in the ELI 5 section. The CPU is more like the head chef coordinating the kitchen so that delicious foods can be made. To do this, it needs to be able to think. Specifically, it needs to be able to do 2 different things: maths and logic. The maths part is pretty easy. We've already covered how abacuses work, and believe it or not, that's essentially how computer maths works. Except instead of base 10, computers use base 2, or binary numbers. And instead of beads, it uses transistor switches that are on or off. But what about logic? How can you ask a computer to check conditions like in an if this then that command? Well, we can use Boolean logic. Way back in the 19th century, a mathematician by the name of George Boole created a system where he could use only true and false to write down almost any logical statement. True can be written as 1, and false can be written as 0. So this system is kind of perfect for computers. By rearranging some of the components of a transistor, we can create special smart switches called logic gates. I mean, I say smart, but the logic is actually pretty simple. Like, you could train a pigeon to be a logic gate. Let's look at some examples. There are 3 basic logic gates: AND, OR, NOT. Each logic gate receives 2 different inputs and generates an output of 0 or 1 depending on the combination of the inputs. An AND gate is super strict. It needs both inputs to be true or 1 to generate an output of true or 1. If you put in 1 and 0, it'll spit out 0. Same with 0 and 1 or 0 and 0. It's like a mum saying you have to do your homework and eat your vegetables before you get ice cream. An OR gate, on the other hand, is much less fussy. It just needs one input of 1 to make the output 1. So chill dad says, you've done your homework, or you've eaten your vegetable, you can have some ice cream. Either or. And of course, if you've done both, that's still a 1. Ice cream for everyone, unless you've done nothing and you've given the OR gate 0 and 0. NOT gate is weird. It's like opposite day gate. Unlike AND and OR, it only takes one input and then flips it. So if you put 0 through a NOT gate, you get 1. If you put in 1, you get 0. Simple as that. Just a stock standard inverter. Now, here's the fun part. You can combine these logic gates to make even more complicated gates. If you combine NOT and AND gates in a specific way, you can make NAND gates, short for not AND. Here, if both inputs are true, or 1, then you get a 0, but all other inputs will give you 1. And in a weird concept called functional completeness, it turns out you can use NAND gates to express any Boolean function. But we have more efficient ways to do this with specific gates, like XOR or exclusive OR. This gate gives you a 1 only if one input is true. So kind of like the OR gate, but if both inputs are true, then you'll get a 0. Then there's the NOR gate. This gate is like AND, but the opposite. So both inputs need to be false or 0 for you to get a 1 output. All other inputs will give you a 0. Your head is probably spinning by this point with all the 1s and 0s, so maybe we'll leave it there for the logic gates. All you need to know is that your computer, specifically your CPU, is using a really complex series of flowcharts made up of these different types of logic gates to follow instructions. Using Boolean logic, you can solve virtually any logical maths equation or problem with logic gates. How, I hear you ask? Well, now we finally get to how your CPU functions, the fetch, decode, execute cycle. Every time your computer is doing, well, pretty much anything, your CPU is cycling through the steps of fetch, decode, and execute. Think of it as the heartbeat of the computer, like looped up, looped up, looped up. Okay, so as you probably gathered from how this episode has been going, you know this is going to be a bit complex, so I'll try keep it as simple as possible, because I assume you're not listening to this podcast to pass your comp sci paper. And if you are, dude, get back to studying after this episode. Alright, so before we break it down, you need to know some names of different parts of the CPU. There's the control unit, which runs the whole shop, kind of like the head chef's mouth talking through all the instructions. There's the ALU, or arithmetic logic unit as Babbage predicted, which has a ton of transistors working hard to do all the maths and logic gate stuff that we just talked about. Think of this as the chef's brain and hands, thinking and doing all the cooking. Then there's the register, which is the super fast storage built into the CPU core so that the CPU can immediately access the bits of information it needs, like the chopping board where the ingredients will get sliced and diced. And of course, remember that CPU chef can't cook without a surface. He needs to put the chopping board somewhere. He needs the prep bench where he can actually store prepped ingredients, get other ingredients to mix in, and so forth. This bench is the RAM, or Random Access Memory. We'll talk a bit about RAM in the next section, but for now, think of it as a very fast memory that the CPU can grab things from quickly to put into its register, rather than having to go all the way back to the main storage like the pantry or the fridge. Cool, so you know the CPU bits and how it's connected to the RAM. Let's go! Like the name suggests, the fetch, decode, execute cycle is made up of 3 parts. Fetch, decode, and execute. Doi. First step, the CPU needs to fetch the information, like a good boy. To do this, it asks the RAM, hey, what's the first piece of data? Grabs it and puts that data in its own register. It's like grabbing an onion from the kitchen bench and putting it on the chopping board so the chef can start prepping it. Once the data from the RAM is in the register, the control unit needs to decode the data. Remember that everything is zeros and ones in a computer. So if the first piece of data in the RAM says 00101110, the CPU needs to know what the heck it's saying to do anything about it. So that's just that. The first half of the data, 0010, tells the CPU what it needs to do with the data, like loading more data onto the next register. The second half, 1110, is the address that tells the CPU where in the RAM to get that data. It's like grabbing an ingredient that has some instructions on it, like a packet of instant noodles, having to read what it says, and understanding it. Alright, so we've got some data, and the CPU knows what the data is instructing it to do. Now we go into the final step of the cycle, execute. The CPU performs the instruction according to the code. If it's something simple like loading data on the register, the control unit does it itself. But if it's more complicated maths or logic stuff, then the ALU gets the job done, like a special kitchen tool, like using a blender or a whisk. And hooray! One computational cycle's done. Now we're cooking. When the cycle's complete, the control unit goes ding and ups the order number by 1, and the CPU gets to the next fetch, decode, execute cycle, fetching the next piece of data from the RAM. The cycle repeats, and the CPU performs more and more tasks. The speed at which the CPU can perform these tasks is the clock speed of the CPU, measured in hertz. If you ever hear that a laptop's processor is 3 GHz or whatever, this is what they're talking about. The higher the number, the more cycles the CPU is doing per second. In the case of 3 GHz, that's 3 billion computational cycles per second. That's so much maths. Modern CPUs are also built in a way where it's not doing the fetch, decode, execute in one long sequential string, but as heaps of parallel processes, like dozens of monkeys all typing away on different typewriters. So if you see that a CPU has 12 cores or has hyperthreading, that means there are essentially 12 CPUs built into one and they're working in parallel rather than in series. So 12 different CPUs all doing 3 billion computations per second each. Wow. Alright, that's a lot to take in, isn't it? Let's do a quick summary starting from transistors, zooming all the way out to how CPUs work. Transistors are teeny tiny silicon switches that can be turned on and off by zapping it with electricity. Switches can be on or off, which can be represented as 1 or 0, meaning you can use binary system maths to turn human speak into computer speak. Computers use the binary system to do all kinds of maths and calculations. We can also use Boolean logic gates to make the computer think logically, solving problems and following instructions that are conditional. All of these switches and logic gates are bundled up in the CPU. They can grab data from RAM, run it through a fetch, decode, execute cycle, and do a computation. Your computer or phone is doing billions of these computational cycles per second, which lets it process everything from showing emails, doing math problems, displaying images and videos, or even running complex programs like video games. Whew! Alright, let's take a break, because we've only talked about the core of the computer, the CPU. We still have some other key players to talk about after we're back. Welcome back. Luckily for us, the CPU is probably the hardest part of the computer to understand. At the same time, it's the most important part of the computer because, well, it literally runs the whole computer. The rest will be a bit easier to explain, hopefully. Let's start with a component that we've already kind of mentioned, the RAM. RAM stands for Random Access Memory, and you'll often hear it just being called memory. Which is strange because you'd think the hard drives with the data stored should be called the memory, right? But remember that human brains also have different types of memory. There's long-term memory, like the stuff we remember for years, like our names, people's faces, and the fact that the mitochondria is the powerhouse of the cell. Oh, never going to forget that. Then there's short-term memory, like remembering what you need to buy when you're at the supermarket. No way in hell you're remembering that 1 year later. In the case of a computer, there's a speed difference between the two different types of memory. Turns out, grabbing data from long-term memory takes a lot longer for a computer. It's like having to walk to the bookshelf, pull out the recipe book, flip to the right page, copy down the ingredients and instructions, and then coming back to the kitchen. Takes ages. Wouldn't it be a lot easier if the chef had it in their short-term memory, or having a copy of that book page on their kitchen bench? This is exactly what the purpose of RAM is, and why we call it the prep bench. It's a super fast memory unit that can give the CPU the data it needs straight away, rather than waiting for slowpoke hard drive to feed the CPU the data, like a super efficient assistant. The reason why it's so fast is because the CPU can ask the RAM for any information it has, and it's available straight away without having to search. This is what we mean by random access. It's like having all of the necessary pages of the recipe book copied out and laid out in a spread, so RAM can pick it out immediately and just go, that one. So yeah, RAM is great, and certainly wouldn't be called an idiot sandwich by Gordon Ramsay. But RAM has some limitations. For one, it's a lot smaller than long-term storage. Most RAM nowadays are somewhere between 8 and 16 gigabytes, whereas most hard drives are in the realm of 0.5 to 2 terabytes, or 1,000 gigabytes. And it makes sense, right? You can't just have all of your pantry and fridge ingredients out on the bench all the time. You need a clean and tidy bench space. RAM is also volatile, not in the sense that it will catch fire, but it's temporary. If you're hard at work on your computer, say writing a 9,000 word podcast script, all of your hard work is being held in the RAM so that the CPU can work on it as it goes. If something tragic was to happen, like the cat chews through your power cord and the computer forcibly shuts down, as an example, all of the data in the RAM gets wiped, like tears in a pizza oven. Whereas if you remember to save as you go, your RAM is periodically sending back the information to your hard drives, where the information is stored securely even when the power is off. And this is your friendly reminder if you're listening to this podcast while doing any work on your computer. Save your work! God knows I've lost so many discharge summaries because someone accidentally logged me out before I had the chance to save it. Oh. Anyway, that's basically how RAM works. Oh, and as you probably guessed, it's doing all that data management and transfer using logic gates. But we won't go into that detail, don't worry. So, if you notice that your computer's running slow when you have multiple apps running, or you have 50 tabs open on Chrome, looking at you, Kelly, it's probably because your RAM is filling up and the kitchen bench is getting too clogged up and messy for your CPU to efficiently work. So if you want to be able to do more at the same time, you want more RAM, like 12 or 16 or even 32 gigabytes, and faster RAM that can process data quicker. Alright, let's tackle the next component, the fattest thing in your gaming PC, the GPU. Now, we've been singing the praises of the CPU, calling it the genius mastermind head chef running the show. It can solve complex calculus, manage intricate databases, and execute any logical task you throw at it. But it works relatively sequentially, which means step by step. It's like a single brilliant professor who solves problems one line of the equation at a time. Sure, we can have multiple cores that can do 12 different tasks at once, but what if we have a task that needs thousands of tasks done simultaneously? This is the problem of graphics, when we convert code into something visual to show the user. Graphics is a bit different to logic and maths that CPU does. Each step of graphics processing is actually really simple. You just need to tell the pixel on the monitor what color to display. Easy peasy, toddler maths. But the problem is when you're playing a high-resolution movie or playing a fancy video game. You need to do an insane number of these processes all at the same time. Even worse, the scene is changing at a rapid 60 or 120 frames per second, so you're doing a heckin' lot of maths at the same time. It'd be like telling the super talented head chef who can do anything from making a Kit Kat souffle, to finely slicing ingredients to a Michelin star level, to cooking up a complicated stir fry, to break open 50,000 eggs every second by himself. Even if it's a super easy task, the sheer number of tasks will overwhelm the chef, which is why CPUs aren't really equipped to handle the graphics side of computers. And that's where the GPU comes in. The GPU is not one brilliant professor. It's an army of thousands of primary school students. It's a processor that's specifically designed for parallel processing, doing thousands of simple, repetitive calculations all at the same time. A modern GPU has thousands of smaller, simpler cores. It can assign a small group of pixels to each core, and they can all perform the calculations simultaneously. This massive parallel power is what allows for the stunning photorealistic 3D worlds we see in modern video games and animated movies. To understand how a GPU works, let's look at the graphics pipeline, the assembly line that the GPU uses to turn a bunch of 3D data, such as a character model in a video game, into the final image you see on your 2D screen. First, we need to do vertex processing. For this, the 3D model, which is just a collection of points in space called vertices, is sent to the vertex shaders. In our kitchen, these vertex shaders are the artists responsible for arranging the main components. They take each vertex or point and figure out where it should be in the 3D world, transforming it, rotating it, and getting it ready for the camera's viewpoint. If you've ever seen actors wearing black suits covered in what look like ping pong balls, this is how they capture where the vertices for a 3D model should be for CGI, or computer-generated imagery. The next step is called rasterization, where the 3D becomes 2D. The GPU takes the triangles formed by the vertices and lays them onto the 2D grid of your screen, figuring out which pixels fall inside each triangle. This is like the artist taking the 3D food components and creating a flat stencil of them on the plate. Kind of like taking a photograph of a 3D cage or a mesh sculpture. Lastly, once the stencil is made from the vertices and triangles, the GPU can color them in with pixel shading. For every single pixel on the screen, a pixel shader runs a tiny program to calculate its final color, taking into account things like lighting, shadows, and the texture of the object. This is where the artists apply all the vibrant sources, the delicate herbs, and the beautiful garnishes to bring the dish to life. This entire pipeline runs many times per second, kind of like the CPU's computational cycle. A game running at 60 frames per second, or FPS, means this entire process from vertices to final pixels is happening 60 times every second for millions of pixels. So you can imagine that's a metric crap ton of calculations. No wonder our CPU wouldn't be able to handle all of that. Instead of one really smart cookie, we just need a lot of dumb cookies doing menial work at the same time. That's right, your GPU is basically a pixel switch shop. Now, remember how the CPU needed to use the RAM as its workbench? The GPU also needs something to work on, so it comes with its own VRAM, or video RAM. The GPU can do all the fancy modeling, texturing, and coloring on this benchtop, so the more VRAM a GPU has, the more work it can do in a given amount of time. GPUs can get really chonky because to run state-of-the-art games with lots of pixels and lighting effects and objects such as Cyberpunk 2077, you need a lot of parallel processing power. So most gamers will have dedicated GPUs in their computers, as in a separate GPU that handles all of the graphics. But for a lot of people who don't game and just watch YouTube videos, they can have much smaller GPUs that are built into the CPU chip, called an integrated GPU. The CPU basically has a teeny tiny GPU sitting next to it to process all of the visuals. Now, the funny thing about GPU is that although the incredible parallel processing power is usually used for gaming, the same simple but tedious maths can be used for all kinds of other things. Scientists will often hook up a bunch of GPUs together to run complex simulations, while AI researchers might use them to train massive neural networks. And let's not forget the Bitcoin miners who used large batteries of GPUs to do the cryptographic maths required to earn Bitcoin, drastically jacking up GPU prices a few years ago. We won't go into what GPU you should buy because that changes year to year depending on what the most current generation of NVIDIA or AMD GPUs are out, and what power level you need for your gaming. I'll let you do your own research there. Anyway, that's about it for graphics. Along with the CPU and RAM, GPU is usually the third and most important thing people look at when buying computers, especially if they have any interest in gaming. But we're not done quite yet. A computer, even the tiny computer in the palm of your hands that you use for messaging and Instagram and memes, has a lot of other components. Let's cover some of those now. Fortunately for you, dear listener, the other components are not nearly as complex as the CPU and GPU and how they work. For example, there's the motherboard, also known affectionately as a MOBO. If the individual components are the kitchen staff, the motherboard is the entire physical kitchen itself. It's the large main circuit board that everything else plugs into. It's the floor plan, the wiring, the plumbing, and the communication system all rolled into one. Basically, it lets all of the components talk to each other and work together to make all of the delicious meals come to life. A MOBO can come in various sizes, such as ATX, Micro ATX, or Mini ITX. They have lots of sockets that different components can plug into. Building a PC is a lot of fun because it's like playing Lego with $1,000 components, and it's really satisfying when everything comes together and works. Pretty frustrating when something breaks though. Anyway, the motherboard has some important functions, such as running the BIOS, which is the first mini program that runs when your computer boots up, to make sure everything is working. Kind of like turning the lights on in the kitchen and doing a roll call. CPU? Yep. RAM? Yep. GPU? Where the frick is GPU? Alright, black screen it is. For the most part, motherboards are pretty stock standard, so the common user doesn't have to worry about what kind of motherboard a computer has, unless you're building a PC from scratch. Next, we have the power supply unit, or PSU. This is the powerhouse of the PC, the kitchen's main power plant and electrical grid. It's basically a glorified transformer that can take the high voltage AC electricity from your wall outlet and tune it to the precise low voltage DC that your computer components need. If you need a refresher on AC and DC, I recommend you listen to the awesome song Thunderstruck, and then our recent episode 61 on electricity. Again, you don't need to worry about what PSU your laptop or phone has because it'll be enough to power your device. But if you're building a PC, you need to make sure your PSU can deliver enough juice to feed the whole PC. Now, remember that all of your computer components are electrical devices, and every electric circuit has some inefficiencies, as the resistance in the conductors causes some heat to be generated. So, we need a way to cool the devices so that the computer doesn't, well, melt. Most devices will have some cooling device, typically fans to circulate the hot air out, but nowadays we have liquid cooling as well. This awesome device sits on top of your CPU and is connected to a bunch of pipes with flowing liquid in it. Don't worry, everything's watertight, so there won't be any leaks inside of your computers, usually. The liquid absorbs the heat from your CPU, carries away into the radiator, vents off the heat, and comes back to the CPU to carry more heat away. There's also a bunch of random components like network cards that let you connect to Wi-Fi and Bluetooth, input and output devices such as microphones, speakers, keyboards, mice, and monitors, but we'll skip over all of those. But lastly, we can't forget storage. The long-term memory where we can store all of our data, from downloaded videos to totally solicited pics like cat memes. In the ye olde days of 90s and 2000s, most computers relied solely on magnetic hard disk drives. Similar to cassette tapes and VHS. Again, probably ancient technology to young listeners, but these drives would store data using
magnets! Oh!
Episode 39 talks all about magnets, so go back and have a listen. That one was a banger. Anyway, hard drives have a reader head that can hover over the disk drive and flip bits between 0 and 1 using magnets. This awesome technology means you don't have to have a gigantic stack of punch cards just to store all of your photos and record them at your whim. But HDDs can be large and clunky, so we're in the process of moving on to a different type of storage called SSDs, or solid-state drives. These drives use electron levels to store data, recording ones and zeros using trapped charges. Using an incredibly dense 3D array of these charge-trapped flashes, or flash memory, SSDs can store a vast amount of data in a fraction of the size and volume of a HDD. If you've seen those teeny tiny microSD cards that can store a whole terabyte of data, that's the same technology as SSDs essentially. SSDs are much faster than HDDs as well because the computer can access the stored bits more on demand, compared to HDDs that have to spin the disk to the right place to pick out the data, like using a Rolodex. But they are still a lot more expensive, which is why most computers will have a smaller SSD to run the operating system and programs off of it for speed, plus a larger HDD to store data that you can wait a few seconds to load. At the same time, technology is rapidly evolving, so HDDs are becoming more and more obsolete. Most laptops and phones rely solely on SSDs and flash memory because it's so much faster, smaller, and lighter. There's even M.2 NVMe SSDs that run even faster, meaning you can transfer massive movie files in seconds. The amount of storage you need depends on how many photos and videos and files you like to hoard on your device. But nowadays, external drives are so cheap and light that you probably only need somewhere between 256 gigs to 1 terabyte on your phone and laptop. The march of progress is incredible in the tech world, and if you're a nerd like me, it's really exciting to see how far we've come. From having to use stacks of floppy drives to install Windows overnight, to having entire libraries of TV shows and movies in a drive the size of my fingernail in my lifetime, is amazing. Also, random side bit, did you know that some kids actually think floppy disks are 3D printed save icons? Ugh, little fools. Anywho, the world of computers is so deep and amazing, we could spend hours talking about how Unicode and ASCII let us encode any letter or symbol in binary, or how Turing machines work, or how programs turn commands into digital action, but then we'd be here all day. So let's wrap it up here and call it an episode. So, what did we learn today? We learned that a computer is a collection of highly specialized components that work together like a busy kitchen to do some incredible computational tasks. We learned about the history of computers and how we've come from mechanical abacuses to handheld devices that can look up anything online in the space of 200 years. We learned about how transistors work and how computers can use these teeny tiny switches to speak in binary, zeros and ones. We learned that CPUs use Boolean logic gates and binary numbers to do all kinds of maths and logic to do all the things your computer does. We learned that GPUs work differently, using parallel processing to draw all kinds of complex graphics on your screen. We learned how RAM, motherboards, hard drives, and PSU work, as well as learning a little bit about what all the numbers mean, Mason. Lastly, we learned that computers are awesome, and there's a lot to learn about them. Alright, for today's 2-minute explain, let's talk about the driving force that has powered the digital revolution for the last 50 years, Moore's Law. Back in 1965, Gordon Moore, one of the co-founders of the tech giant Intel, made a simple but profound observation. He noticed that the number of transistors that engineers could fit into a single integrated circuit was doubling approximately every year. A few years later, he revised his forecast to doubling every 2 years. This observation, which became known as Moore's Law, wasn't a law of physics per se. It was more of a prediction based on the current trends of how technology develops, a self-fulfilling prophecy, if you will, for the semiconductor industry. It became the goal or benchmark, the roadmap that drove innovation. For decades, engineers worked relentlessly to keep up with this pace, and they succeeded. The implications of this are staggering. Doubling the number of transistors means you're roughly doubling the processing power of a chip. And because of economies of scale, you're doing it while the cost stays the same or even goes down. This exponential growth is the reason why smartphones in your pocket today are millions of times more powerful than the room-sized computers that guided the Apollo missions to the moon. It's why we have laptops, video games with photorealistic graphics, and the entire internet. Moore's Law is the engine of technological progress. However, this incredible run might be coming to an end. We're now finally bumping up against the fundamental limits of physics. Transistors are getting so small, measured in just a handful of atoms, that they're becoming difficult to control. You see, when you go down to the atomic scale, quantum physics takes over and some pretty weird things can happen. For transistors, the problem is something called quantum tunneling, when electrons can basically teleport from one place to another when the distance between them is small enough. This makes transistors useless because you can no longer stop the electrons in the off state, and the transistor is functionally on all the time. No more binary states, no more computer. So, is the party over? Not quite. The industry is now looking for new ways to keep the progress going. Instead of just making transistors smaller, they're finding clever new ways to stack them in 3 dimensions, designing more specialized chips for specific tasks like GPUs for AI, and exploring entirely new paradigms of computing like quantum computers. Moore's Law, as we knew it, might be slowing down, but the human drive for innovation that it represented is still going strong. The digital kitchen is just finding new recipes for getting faster and smarter, and I love learning all about it. Well, that's it for today. Thanks for listening to Explain This. I hope you've learned something interesting and maybe even useful today. Maybe now you know what kind of specs to look out for when you're buying your next phone or laptop. Or, at the very least, have more of an appreciation just how much power we carry in our pockets nowadays. I'm still not sure at the end of this episode if it's too technical and complex for listeners who aren't into computers to enjoy it, so I'd love to get some feedback whether you like these kinds of episodes or not. I mean, the podcast is literally about taking complex concepts and explaining it in simple ways, but sometimes I do bite off a bit too much to chew. At the same time, if there are topics that you are really interested in but feel like it's too complex for you to wrap your head around, please send it to me as a topic suggestion and I'll try to tackle it. We'll see you next time. Bye for now. Explain This is written and hosted by me, Jin Kim. If you'd like to suggest a topic or just send a lovely message, you can email me at explainthiscast@gmail.com or follow me on social media on Facebook, Instagram, or Blue Sky.